Okay, so we're doing hold on. All right. So we're doing the inverse of a matrix. Now, I got something cool. Boom. So this is going to be the best of both worlds. I'm going to be able to write down the problems and stuff like that, but I also get to stay seated and it's going to be easy. So anyways, we're going to do that for the exercises. All right. Let's get into it. We're going to just do some quick notes and then do the problems and then get out of here. Yeah, I got a lot to do. Matrix algebra provides tools for manipulating matrix equations and creating various useful formulas in ways similar to doing ordinary algebra with real numbers. This section investigates the matrix analog of the reciprocal, or multiplicative inverse, of a non-zero number. Recall that the multiplicative inverse of a number such as 5 is 1/5, or 5 to the minus 1. This inverse satisfies the equations 5 to the minus 1 times 5 is 1, and 5 times 5 to the minus 1 is 1. The matrix generalization requires both equations and avoids the slanted line notation for division. Because matrix multiplication is not commutative. Furthermore, a full generalization is possible only if the matrices involved are square. An n by n matrix A is said to be invertible if there is an n by n matrix C such that C times A is the identity and A times C is the identity. In this case, C is an inverse of A. In fact, C is uniquely determined by A because if B were another inverse of A, then B is equal to B times I. Wait, hold on. It's equal to B times AC. It's equal to BA times C. Okay, so this is an interesting proof. Okay. So the proof that a matrix is unique. Inverse is unique. If okay. Okay, so we just say A to the minus 1 is the inverse. A matrix that is not invertible is called a singular matrix. Okay, here's an example where we verify it. Okay, the definition of determinant and the formula for the inverse. An example. Okay, the proof. A horizontal elastic beam is supported at each end and is subjected to forces at points 1, 2, and 3. Let F in R3 list the forces at these points, and let Y in R3 list the amounts of deflection. That is, movement of the beam at the 3 points. Using Hooke's law from physics, it can be shown that Y is equal to dF, where D is the flexibility matrix. Its inverse is called the stiffness matrix. Whoa, that's weird. Describe the physical significance of the columns D and D inverse. Interpret the vector E1 as a unit force applied downward at point 1 on the beam, with 0 force at the other 2 points. Then DE1 is the first column of D. It's the beam deflections due to the unit force at point 1. Oh, for a given deflection, we can calculate the force with the inverse, with the stiffness matrix. It's cool. Now interpret U. To create the deflection. That is, the first column of D inverse lists the forces that must be applied Okay. An elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. If an elementary row operation is performed on an m by n matrix A, the resulting matrix can be written as E times A. So wait, if an elementary row operation is performed on an m by n matrix, A, the resulting matrix can be written as E times A, where the m by m matrix E is created by performing the same row operation on M. On I. Since row operations are invertible, elementary matrices are invertible. So for if E is produced by a single row operation on I, then there's another row operation that of the same type that changes E back into I. Hence, there is an elementary matrix F such that F times E equals I. Since F and E correspond to reverse operations, EF equals I, so they're inverses of each other. Each elementary matrix E is invertible. So let's get the definition. Let me write this down. The following theorem provides the best way to visualize an invertible matrix. That's actually really cool. That's really cool. I like that a lot. That's pretty neat. Yeah, you can do this. This is neat. Row reduction is so cool. Let's try to do this in Okay, so using linear algebra, where are my usings? Where is it? Here we go. Um, let's see. Mm. I wonder if that's gonna work. Dude, why is this thing always so slow? Oh, that's so cool. That works, man. Heck yeah. That is very neat. So then that's A inverse. That's super cool. Another view of matrix inversion. In practical work, A inverse is seldom computed unless the entries of A inverse are needed. Computing both A inverse and A inverse B takes about 3 times as many arithmetic operations as solving AX equals B by row reduction, and row reduction might be more accurate. Okay. It's time to do some practice problems. It's kind of annoying. I won't be able to, like, have both up at the same time. So I guess I'll just write them down first. Okay, so let's do the first one. It'll be our first time doing this thing. This will be cool. So okay, so the first one is invertible. All right. Problem 2. I think we're just going to, for this one, we're going to do this. Or we'll do the RF HCAT AI. Okay, it is not invertible. So what I'll do here is we will write HCAT or RF HCAT AI has an empty row for this. A not invertible. Yeah, there's a free variable. And if there's a free variable, it's not gonna, they're linearly dependent, right? Or, yeah, it's linearly dependent. Okay, number 3. If A invertible, then 5A invertible. Oh wait, we need to This is not right. This is minus 5c minus 5b. What is the formula for A inverse? The formula for a 2 by 2 inverse is, yeah, minus b minus c. Okay, so we proved it for 2 by 2, but I don't know if that's general. I'm guessing it is. So that means that this is going to be 5 inverse. Wait, 5a inverse is equal to 1 over 5 inverse. And also, well, we could just do this. So 5a times 5a inverse, we know is going to be I. Well, I guess we don't know it. We're trying to prove it, but oh, you know what though? I'm pretty sure. I don't know if they showed this in the thing, but if we have, let's say, R and R, then for R A inverse is equal to A. I believe this is just going to be R inverse A inverse. But I don't know if that's true. Let's see what the answer is. Yeah. So it is what I said. Okay. All right, now let's look through the problems. See if there's any good ones. Find the inverse, verify the inverse, use the inverse to solve a system. Okay, so we'll do 1, 5, and 7. Let's see, 2.2 exercises. It's going to be 1, 5, 7. Now let's look through 9. Find A inverse, use it to solve 4 equations. The 4 equations in part A can be solved by the same set. The 4 equations in part A can be solved by the same set of row operations. Since the coefficient matrix is the same in each case. What? Solve the 4 by row reducing that. Yeah, okay, fine. 9 makes sense. I don't know if I'm going to do it. Use matrix algebra to show that if A is invertible and D satisfies AD times is equal to I, then D is equal to A inverse. Ten is good. We'll do 10. All right, I like the true falses. I always like the true falses. So we're going to do 11 through 20. Let A be an invertible n by n. Let B be an n times P matrix. '21 seems pretty good. Let A be an invertible n by n. Let B be a n by p. If A, B... I like 21 and 22. Is good. These are all good. Yeah, suppose B minus C times D is 0, where B and C are m by n, and D is invertible. Show that B is equal to C. Suppose A, B, and C are all invertible. Show that A times B times C is also invertible. That one's easy, but we could do that one. But yeah, I like that one. I like all of these. All of these ones are really good. That's why it's nice to read all of them at least, because then you have an idea. I suppose A and B are n by n, B is invertible, and AB is invertible. Show that A is invertible. That's pretty good. – 26 and 27 are good. I always end up just writing them all down. Suppose P is invertible and A is equal to PBP inverse. If A, B, C are invertible, oh gosh. Okay. So 30, suppose A, B, and X are n by n, and A and X and A, this is going to be, this should be A minus I, or wait, no, this should be I minus X times A. I mean, it doesn't really matter if it's it should be a times I minus x, I think, and then it distributes. So suppose explain why b has to be invertible. Solve 3 for x. Explain why the columns of an n by n matrix A are linearly independent when it's invertible. Dang, all of these problems are so good. I mean, if it's invertible, it's row equivalent to the identity matrix, which is linearly independent for sure. So that's probably the simplest answer. Explain why the columns of an n by n matrix span Rn when A is invertible. I mean, if the columns are linearly independent, then they span the codomain. We could check that one, but I'm almost positive that's the answer. Suppose A is n by n, and Ax equals 0 only has the trivial solution. Explain why A has n pivot columns and A is row equivalent to In. So if it only has the trivial solution, then it spans Rn. If it spans Rn, it's going to have n pivot columns. I'm pretty sure if the columns of a matrix, a square matrix, are linearly independent, then it's invertible, right? Did they say that? And anything that spans the code. Okay. All right, I'm pretty sure that's true. Suppose A is n by n, and Ax equals b has a solution for each b in Rn. Explain why A must be invertible. That one's really good. Okay. Prove theorem 4 for A. Yo, what's up? Wait, hold on. What the hell is going on with my chat? How do you know an invertible matrix? Because, yeah. Oh, yeah. Sorry about that. There we go. Okay. 35. We're going to do all these exercises in a second here, but right now I'm just reading through all of them to get an idea of what's in this section. Show that if the determinant is 0, then the equation Ax equals 0 has more than one solution. Ooh, 35 is good. I like 35. Why does this imply that A is not invertible? If Ax equals 0 has non-trivial solutions, then the columns of A are linearly dependent. Okay, I don't really get this last part there. 36, show that if it's not, the formula for A inverse works. I mean, show that it works. I don't even know what that means. Works as an inverse? '37 and 38 prove special cases of the facts about elementary matrices stated in the box following example 5. Okay, this one's obvious. This one's obvious. Because row I of the identity matrix is just going to be n zeros with a 1 on the ith position. So it's going to be plucking out, for each row column product, it's going to be plucking out the ith element of each column of A. So show that if rows 1 and 2 of A are interchanged, then the result may be written as EA, where E is an elementary matrix formed by interchanging. You know, this one's actually interesting because the definition of elementary matrix was a single row operation, but I don't know how you can. Oh, I think that they defined the elementary row operations as a swap. Like, a swap counts as 1. So in that case, the permutation matrix that permutes the rows. And what does that look like? It should look like the identity with just the first and second rows swapped. Oh yeah, there you go. Okay, that one's easy. Show that if row 3 of A is multiplied by 5, if row 3 of A is multiplied by 5, then the result may be written as E times A, where E is formed by multiplying row 3 of I by 5. So for that, it's just obviously true. Think about the row column products. It's like the last element is a 5, so then the last row of A is going to be 5 times whatever it was. 38, show that if row 3 of A is replaced by row 3 of A minus 4 times row A1, and the result is... Okay, maybe that one's a good one. 38. So wait, which ones did I want to do? 35. 35 was good. 36. I didn't really understand 36. Show that if the determinant is non-zero, then the formula for A inverse works. I mean, I don't know what they're trying to say, but the formula for a 2 by 2, which is what they're giving us, has that determinant as the denominator of a fraction. So if it was 0, then it wouldn't work. So I think we can skip that one. 38 I wanted to do though. 37 we just did it. I mean, we don't really need to show much more than that. We can skip all of these. Use the algorithm, find the inverses of those. We can skip all of those. Well, you know what? Maybe we'll just use a computer to do them, just to look at them. Is there a lower triangular? Is there a way to get a lower of like 1? I think this is a. So wait, what about ones, 3 by 3, and then we do lower, and then we do the inverse of that. Okay, so this was number. This is number 43. That's kind of interesting. All right, I guess it works. Actually, kind of makes sense. Wait, what about the 4 by 4? What did the 4 by 4 look like? Okay, it's still. Is that right? Okay. Is this that Vandermond? No, I think this is like. Wait. No, this is not. Because this squares it. But I think that there's got to be a special name for this. Um, 44 might be kind of fun, actually. Find the third column. 45? I don't know how to do that. Find the inverse without, hello. Y2 angles. Oh, check this out. Watch this. When I start doing the problems in a minute, we can start doing, the homework right here so that you can see what I'm working on. But for right now, we're just reading them. 45 seems cool. I totally want to do one of these. These applied problems are the best problems in the thing. Okay, so let A be that. Construct a 2 by 3 matrix C. $47 seems good. $48. I don't know about that. Such that AD I would like to know the Y. Okay, here's a flexibility matrix. So what does this mean? If I apply, so we have this beam here. Let's just say it has three. It has 3 points. If I apply a unit vector of force to, let's see, if it's just 1, 0, 0, then the force. Oh, okay, so it's oh wait, no. I did this wrong. Oh, but it is a symmetric matrix. I guess that makes sense, kind of. Is this one symmetric? Yeah, it's symmetric. Okay. I know. Hey, what's up, Riley? Dude, I didn't even notice it was you, Riley. That's weird. I don't know why I didn't notice that. I know I need a. Well, actually, you know what? I have a. Hold on. Let me get my charger. I'll be right back. Okay. Okay. So I have this thing. Let's see if this thing is gonna work. Did it work? All right. So I can use my phone now. So my phone is my Steam Deck or Stream Deck. What's up, Anuri? Okay. So wait, we are on the wrong scene. Okay. So here we go. Compute the stiffness matrix. So wait, we need to review the definition, but we're definitely going to do 49, 50. Um, so flexibility matrix, I'm guessing. What was the definition again? Let's duplicate this. Okay. Now here we go. Okay, so D is the flexibility matrix. So for a given vector describing the forces at each point, okay. Wait, how's my volume? Okay. So given a vector of forces at the points, we can compute how far the beam is deforming. Okay. So if it's an equally distributed load, okay, all right, that makes sense. Measurements of the 4 points show deflections of that much. Determine the forces. So, okay, so yeah, 51 is really good because it requires you invert it and then you solve it, but it's a real problem. With D as in, so determine the forces that produce. All right, and we'll do 52. Okay, so we just read through every exercise. It's time to actually do them. Okay. All right, let me also do this really quickly. So I'm just gonna write down all the problems that I need. 1, 5, 7, 10, 11 through 20, 11 through 20, 11 through 35. Wow. 38, 44, 45, 47, 48, 49, 50 through 52. Okay. Now we have all our problems. Let's get started. So for problem 1, find the inverse. And I just want to make sure that it's like all right. So inv of this is going to be equal to 1 over the determinant is going to be 16 minus 6. All right, I'm just going to double check. Okay, so A is equal to 8352 inv A. Wait. Oh, because I wrote it down wrong. This needs to be minus 5. So we get 16 minus 15 is equal to 1. This is 1 over 1. So this is the matrix. 8 minus 5 minus 3, 2. 2. Oh, wait, we're not doing 2. We're doing 5 now. Verify the inverse is correct. So we're going to multiply it with A. So we're going to get 64. Wait. Did I do it wrong? Oh yeah, I did. So the formula for inv A is actually going to be 2, 8. So this is going to be a 2, this is going to be an 8. So this is going to be 2 and 8. So this is a 2. Still, that doesn't seem right. Because that would be 16 minus 9. Wait, what the hell is going on here? I must have written something down wrong again. Hey, yeah, if you want to find this textbook, just look up linear algebra and its applications PDF. I just looked it up with PDF. Just Google it and you'll find it. Thanks for the comment. That's really nice. I just look up that. You'll probably do them faster than I am. I'm going slow as a snail today. 8, 5, 3, and 2. Wait, how have I got this so wrong? Oh, Jesus. No, yeah, 8352. Then A inverse 2. Oh, wait. Did I? No, I think I messed up the formula again. Okay, let me just write it down for real. Yeah, oh, okay, I confused it. Yeah, so if A equals A, B, C, D, A to inverse is equal to 1 over AD minus BC times D minus B minus CA. Okay, there we go. So let's start it over. So A inverse is then going to be equal to 1 over 16 AD minus 15 BC. And then this is going to be minus D. So this is going to be just D. So this is 2. This is going to be minus B. This is minus 3. This is going to be minus 5. And this is going to be 8. Is equal to 2 minus 3 minus 5 and 8. Hold on. I'm going to pull up the chat so I can see it on my phone. Okay. But yeah. No, it'd be cool to have people to work on these problems with. All right, so this is the answer for the inverse. Now we verify the inverse. So we're going to do 8, 3, 5, 2, 2, minus 3, minus 5, and 8. This is going to be equal to 16 minus 15. There we go. Now we're starting to get numbers that look right. Then here we're going to get minus 24 plus 24. Then we're going to get 10 minus 10. And then we're going to get minus 24. Wait, no. Hold on. Minus 15 plus 16. So this is going to be equal to 1, 1, 0, 0 is equal to the identity. Now we actually have to verify the other way around, I believe. So it's going to be 16 minus 15 again. So this is going to be 6 plus 6, or 6 minus 6. This is going to be minus 40 plus 40, and finally minus 15 plus 16. Okay, we finally did the first two problems. Okay, great. Now we want to do, let's see, which problem is next? Number 7. Okay, so number 7 is use A inverse to solve AX equal to 2 minus 1. So if we have AX equals B, we can multiply both sides by A inverse, and we're going to get A inverse AX is equal to A inverse B, which is equal to X is equal to A inverse B. So if we multiply our inverse, which is equal to 2 minus 3 minus 5, 8, times 2 minus 1, we're going to be equal to 4 plus 3, 7, and this is going to be minus 10 minus 8 minus 18. All right, I'm going to verify that on the calculator. So let's do that. So let's see. We'll just double check my work with a backslash 2 comma minus 1. Okay, I got it right. So we're good. All right, the next problem is number 10. Okay, number 10 says, show if A invertible and A times D is equal to I, then D equals A inverse. Okay, so this one's actually going to be, oops, you can't see my, I'll move it down a little bit. Okay, so here's what we're going to do. We're going to take A times D equals I, and we're going to multiply A inverse. So we're going to get is equal to A inverse A times D is equal to A inverse times I. Now, we can regroup this by the associativity of matrix multiplication. So we're going to get A inverse A times D is equal to A inverse I. Now, A inverse I, by the definition of the identity, and just by computing it, you're going to get A inverse. And then this, A inverse times A, we know A is invertible. We know that this is the identity. So ID is equal to A inverse. So D is equal to A inverse. Okay, that concludes number 10. Okay, wait, which is the next one? Let me consult my list here. Yeah, okay, so we're doing 11 through 35. But these true falses are good. Okay. Here, I'll switch scenes so that we can talk about this. So we're going to do 11 through 20 just on the computer, probably. So, true, false. In order for a matrix B to be the inverse of A, both AB equals I and BA equals I must be true. That is true. So 11 is true. A product of invertible matrices is invertible. And the inverse of the product is the product of their inverses in the same order. That's false. It's reverse order. You need to reverse the order. Okay. Number 13, if A and B are invertible, then A inverse times B inverse is the inverse of AB. So this is the exact same one as 12, and it's false. 14. If A and 14, if A is invertible, then the inverse of A inverse is A itself. That's true. Double inverse equals itself. 15. This is the wrong formula for the determinant. This is false. If AD equals BC, then A is not invertible. That's true. That's true. Because if you move the BC, wait, hold on. If you move the BC to the other side, then you get the determinant, and if the determinant is 0, then it's not invertible. If A is invertible, then AX equals B is consistent for each B in Rn. That is true. That is true. Because, and here's one way of saying it. If it's invertible, then it's row equivalent to the identity matrix. If it's row equivalent to the identity matrix, then it must span the codomain, which is Rn. Therefore, there is some vector x such that the action of A on x is equal to B for all B in the codomain, by the definition of span. So that one's easy. Okay, 18. If A can be row reduced to the identity matrix, then A must be invertible. That one might be tricky. Let me think. No, that's just true. Every elementary matrix is invertible. That's true. If A is invertible, then the elementary row operations that reduce A to the identity. No, see, this is false. They got it flipped around. Because what it actually does, if the row operations that reduce A to the identity reduce the identity to A inverse. Which I really like that. I really like that theorem. Oh, we're on the wrong scene. I thought it worked. Sorry. My bad. Okay, so now that we have all of our answers, we should be able to just take a screenshot. All right. True, false, false. I want to go back to this and see. Okay. True, false, false, true, false, true, 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 false. Okay, we got them all right. Those were pretty easy. Okay. Moving on, then. Okay. Number 21. Let A be an invertible n by n matrix, and let B be an n by p matrix. Show that the equation A times x equals B has a unique solution. well, this is like the most applied field of mathematics. The number of applications, I'll just give you an example from this section. If you want to calculate the deflection of a beam using Hooke's law, well, if you have a bunch of forces on the beam, you can create a flexibility matrix or a stability matrix for, what do they call it? A stiffness matrix. And so you could figure out if your bridge is going to break. Linear algebra is very full of applications. Okay. Let's get back to doing. Oh, it lost connection. That's why. See, that's the thing about the OBS blade. It just doesn't really work. Okay. All right. So A is invertible n by n matrix. Okay. And we want to show that show AX equals B has a unique solution A inverse B. So the first thing is AX equals B, A inverse is going to be equal to X equal to A inverse B. But this, so it's going to be N by P. This shows that X equals A inverse B, but not that it's unique, right? It's always actually really good to see how ChatGPT answers these because ChatGPT is so smart. So this is existence. Okay, so that shows that it's a solution. So if you do, so this does show it's a solution, but we plug it back in just to double check. So you do, so you get back the original equation, which is AX, which becomes A inverse B is equal, is A times A inverse B equal to B. So then this is equal to A inverse, B, equal to B. These cancel, and then we're good. So this is existence. Now uniqueness. Suppose X is any solution. Now you suppose it's any solution and you multiply by A inverse and you get X equals. Okay. All right. 22. Let A be an invertible n by n matrix and let B be an n by p. So explain Okay, so we have a matrix AB, and we row reduce it to IX. So what this means is when we do this with AI, and then it goes to IX, in this case, X equals A inverse. So here, this is equal to B, uh, what is that? Hold on. They're saying X in this case is equal to A inverse B. That's a good one. But why? I really like that theorem, though. This is like the coolest thing ever. Oh, shoot. So in this case, you get EK minus 1, E, A, so. Oh, yeah, so this equals A inverse. There, hold on. EK E1B is equal to A inverse B. Okay, so that actually checks out. I really like that. Okay, we're doing number 23 now. Suppose AB equals AC. Okay, so we have AB is equal to AC. B comma C are both N times P. And A is invertible. Show B equals C. Is this true if A not invert? Okay. All right, number 24. Suppose B minus C times D is equal to 0. B, C are M by N, D invertible. Show B equals C. Okay, so here's what we're going to do. We're going to use the distributivity. I think it's called the right distributivity of matrix multiplication, and we're going to get BD minus. Wait, is that true? Because if that's the case, I don't know how to unwrap this thing. Because if we had dB equals dC, then I would apply D inverse, and we would get B equals C. I'm going to go back to the notes really quickly, and I'm going to look at, in matrix algebra, we had a bunch of rules. We're going to look at the right distributivity. Okay, so I did apply the right distributive law correctly, but I don't know how we can now show. We know D is invertible. Am I allowed to multiply to the front? Ugh. Okay, so you can actually multiply on the left or the right. I don't know what the proof of that exactly is, but that means that we can actually use this D inverse on, so we're going to multiply by D inverse, and we're going to get B, D, D inverse is equal to C, D, D inverse is equal to B is equal to C. Okay, cool. All right. All right. 25 says, suppose A, B, C invertible. Show A, B, C invertible. By making D such that A, B, C, D is equal to I, and D, A, B, C is equal to I. Okay, actually, this is a good problem. Let D equal C inverse, B inverse, A inverse. Then we're gonna get A, B, C, C inverse, B inverse, A inverse. By associativity, we can group these so that we have AB times C, C inverse, times B inverse, A inverse. Now you can probably see what's going on here, because we're going to get this cancels, and then these cancel, and then these cancel, and we get I. So similarly for the other way, we're going to get C inverse, B inverse, A inverse times A, B, C, and then these cancel, and these cancel. So that's cool. I like that one. That one was fun. Okay, 26. Suppose A and B are n by n, B is invertible. Show A is invertible. The hint is let C equal AB and solve for this equation for A. Okay, so C is equal to AB. So then CB inverse is equal to A. Which means that this is going to be AB. Wait. Wait, I don't know how that shows the invertibility of solve that equation for A. So when we get that equation for A, we're going to get B times A times B times B inverse equals A. Then we just get A equals A though, right? No, I don't get that one. Here's the answer. There is a theorem that if A invertible and B invertible, or A invertible and B invertible, then AB invertible. So, since C inv and B inv, then C, B, and if B inv, then B inverse is inv. So then so therefore this product of invertible matrices. So we get A times B inverse is inv, but this is equal to A, so A must be inv. Pretty cool stuff. All right, what's our next problem? $27. Okay. A, B, C invertible. And AB equals equals BC. AB equals BC. So what we're going to do is multiply by B inverse. So we're going to get A is equal to BC B inverse. Is that it? That might just be it. Yeah, that's it. Okay. That one's easy. 28. P in and A is equal to P B P in. Solve B. Solve B in terms of A. So let's first multiply by P. So we get A equals PB inverse. We multiply by P. We're going to get AP is equal to PB. Then we're going to multiply by P inverse. And on the left this time, we're going to get P inverse AP is equal to B. So let's just double check the answer. All right, cool. That's it. Yeah, those problems are really simple. So that was correct. All right. 29. If A, B, C are invertible, does C inverse times A plus X B inverse equal IN have a solution? Okay, let's think about that. So the first thing we can do is we can just unwrap this. So we multiply both sides by B, and we get C inverse A plus X is equal to B. Or this is going to be IB, but the thing is IB equals BI equals B. So we're good there. Then we multiply by C, and we're going to get A plus X is equal to CB. But also we could have done C inverse A plus C inverse X is equal to B. Then we could have done, and does it have a solution? Does it mean, does the equation have a solution X? Okay, so we're trying to solve for X. All right, so here's what we're going to do. Then we're going to get, so X is equal to CB minus A. And then we could try it this way, where we get C inverse X is equal to B minus C inverse A. But then we're going to multiply both sides by C. And we're going to get X is equal to C B minus C inverse A. X is equal to CB minus C inverse A. X is equal to CB minus A. Okay, cool. So yeah, it does. All right, take a 5-minute break. hop back into it in a second. Man, life too good, bro. Life a little too good. All right. This is an 8-minute break. It was a little long. Okay. What are we doing here? 20. We did 28. We did 29. 30. Time for 30. 30. So we have A, B, X, N by N. A, X, and A minus AX invertible. So we want to, okay, A. Suppose A minus AX inverse is equal to X inverse B. Then we want to show B invertible. Okay. Okay, so my general idea was to show that if B is a product of known invertible matrices. Wait, actually, what am I talking about? This is super easy. We have this invertible because product of invertible. So, and this is equal to B. So that's all we have to do. So to rewrite it, we're going to get, we have A minus AX inverse is equal to X inverse B. We multiply both sides by X, and we get X on the left. So these cancel, and we get X times A minus AX inverse is equal to B. This is invertible because it's given, this is invertible because this is given as invertible, so its inverse is also invertible. So then B is invertible. Okay, great. I'm gonna ask ChatGPT, but I'm pretty sure that's true. All right. Do 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 do. All right. No, they invert both sides, so they get A minus AX equals B inverse X. Oh, that helps it out. Yeah, that's how you should do it. Okay, from there we can probably figure it out, right? Oh, silly goose. Okay, I get it. This is what we need to do. So for A minus A x inverse equal to x inverse b. We take the inverse and we get a minus ax is equal to b inverse x. Then we get a is equal to ax plus b inverse x. Then we get a is equal to a plus b inverse times x. So then we multiply, so then we get x is equal to a times a plus b inverse inverse. That was a tough problem. Wait, what did I do wrong? Oh, wait, I did do it wrong. Yeah, okay, there we go. All right, that was a good one. Okay. Calls of A linearly independent if A inv, because A is row equivalent to I, which is independent. Let's see how ChatGPT answers it, but that's my answer. Explain why the columns are linearly independent when A is invertible. Okay, so their solution is that you that if A invertible, then A C equals 0 only trivial solution. So because we get C is equal to A inverse 0 equal to 0. And calls A indep when AX equals 0 only. All right, let me reevaluate because we've been doing this for a long time. Let's see, what else do we need? We skipping those, What are we on? We're on 31. 32. Explain why the columns of an n by n matrix span Rn. Well, I think we did that one. if they're linearly independent, then all right, let's just move on to 49. Let's just go back to the definition again. For the beam bending, a flexibility matrix takes forces and returns the. So this is just going to be y deflection is equal to d times f. So we don't need to compute this, but this is the answer. Now 50 compute stiffness D inverse. Then list forces to produce deflection of 0.04 inches. Okay, so what that's going to be is that's going to be compute D inverse times at point 0.3. So this is going to be 0.04. Okay, so I'm going to do this. We have D is equal to 0.005, 0.002, 0.001, 0.002, 0.004, 0.002, 0.001, 0.002, 0.005. Okay, so for the problem 49, it's going to be D times 30, 50, and 20. So it's going to deflect less than an inch. Okay. This is 49. Then ND times for that much, it's going to be very little. Okay, so this is going to be equal to 0 minus point. Wait. Is that right? That doesn't seem right. How do you have a negative? I guess that actually makes sense. You kind of need to lift it up if all right, I think we're good. All right, so that is the section on matrix inverses. We are done. So we're going to I'm going to probably do the homework, then I have a test to do, but I'm really liking this I'm really liking this thing. I think it's a vibe. It's a vibe, dude. Just doing homework outside. I think the camera makes it look so good. Honestly, the camera quality on my OBS makes it looks way better than but still I think it's a total vibe and I'm so down for it. And I think this is going to be very fun going forward. We do a bunch of textbooks like this and it's just a vibe, dude. The sunlight on the paper, I just think it's beautiful. Linear algebra in the sunlight. All right. Peace out.